On November 14, 2023, Voyager 1 stopped functioning normally, transmitting only a meaningless stream of binary data. It seemed like the spacecraft, which had ventured beyond the solar system, was lost forever. The issue turned out to be a memory failure in its onboard flight data system, FDS, putting the mission at risk of permanent communication loss. However, the team of scientists refused to give up. They made a bold decision to reallocate code to other parts of the probe's memory. This risky process began on April 18, 2024, and was challenging due to the 22.5-hour delay for signals to travel to Voyager 1 and the same time for responses to return. Each step was filled with uncertainty, but just 2 days later, after months of effort, Voyager 1 re-established contact. The history of the Voyager missions is filled with incredible achievements. In the late 1970s, a rare planetary alignment occurred, an event that happens only once every 175 years. This unique opportunity allowed NASA to study the gas giants, Jupiter, Saturn, Uranus, and Neptune, in a single mission. Voyager 1, launched shortly after Voyager 2, overtook its twin thanks to a faster trajectory, reaching speeds of 38,000 miles per hour compared to Voyager 2's 34,360 miles per hour. Just 13 days after launch, Voyager 1 captured a historic photo of Earth and the Moon from 7.2 million miles away, symbolizing the start of its grand journey. In 1979, both probes reached Jupiter. They revealed the planet's faint rings, discovered 3 new moons, and captured detailed images of its largest satellites. Notably, they confirmed that Ganymede, not Titan, is the largest moon in the solar system. Voyager 1 also showed Europa's smooth, cracked ice surface, leading to the hypothesis of a subsurface ocean. The spacecraft provided the first close-up view of Jupiter's Great Red Spot, a centuries-old storm larger than Earth. Using Jupiter's gravity for a speed boost, both probes continued to Saturn. Voyager 1 reached Saturn in 1980, while Voyager 2 arrived in 1981. The mission's initial goal was to study Jupiter and Saturn for 4 years, but NASA had designed the spacecraft trajectories for potential exploration of other planets. Voyager 1 focused on Titan, the only moon in the solar system with a dense atmosphere, sacrificing its ability to travel further. Meanwhile, Voyager 2 continued to Uranus and Neptune. The probes delivered detailed images of Saturn's rings, revealing their intricate structures, and discovered 4 new moons. Mimas, one of Saturn's moons, gained attention for its massive Herschel crater, giving it a Death Star appearance. Titan's thick atmosphere, opaque to visible light, posed a challenge, but analysis suggested conditions where methane behaves like water does on Earth. After Saturn, Voyager 1's trajectory changed, making it the fastest spacecraft in history, while Voyager 2 proceeded to Uranus, arriving in January 1986. Unlike Jupiter and Saturn, Uranus is an ice giant with an ocean of water, ammonia, and methane beneath its atmosphere. It's the coldest planet in the solar system, even colder than Neptune. Voyager 2 then moved on to Neptune, arriving in August 1989. It captured detailed images of the planet, which appeared vividly blue, although later analysis revealed its color to be closer to teal. Neptune remains the farthest planet ever visited by a spacecraft. Meanwhile, Voyager 1, after its Saturn mission, had most of its instruments turned off, leaving only tools to study the surrounding environment. In 1990, it captured the famous pale blue dot image of Earth from 3.72 billion miles away, a symbolic last photograph before its cameras were permanently shut down. In 2012, Voyager 1 crossed into interstellar space, marked by a drop in solar particles and a rise in galactic cosmic rays. Voyager 2 followed in 2018. These milestones indicated that the probes had exited the heliosphere, the solar system's protective bubble formed by the sun's solar wind. The boundary between the heliosphere and interstellar space, known as the heliopause, revealed surprising data. Scientists previously believed the solar wind would gradually weaken, but instead, it ends abruptly at a sharp boundary where it changes direction. Beyond this boundary, interstellar plasma interacts with the solar wind, creating a dynamic and constantly shifting region. The Voyagers also uncovered mysteries about the solar system's boundary. The temperature and density of solar wind particles near the heliopause were much lower than predicted, leaving scientists puzzled. They found that interstellar space contains colder, denser plasma, while the plasma near the heliopause is hotter and less dense. The interaction between these two regions forms a boundary layer that scientists are still trying to understand. Shock waves from the Sun can pass through the heliopause into interstellar space, creating disturbances similar to those caused by supernovae. Additionally, the interstellar magnetic field was found to be much stronger than expected, exerting more pressure on the heliosphere than previously thought. In 2022, Voyager 1 transmitted a strange signal while 14.6 billion miles away, consisting of chaotic data about its position. This issue was traced to a malfunction in its attitude control system, likely caused by cosmic radiation. Engineers resolved the problem by rerouting telemetry through another onboard computer. Another challenge arose in November 2023 when Voyager 1 fell silent for 5 months due to corrupted code. The team successfully reallocated the code to other parts of the spacecraft's memory, restoring communication in April 2024. Despite their resilience, the Voyager's missions are nearing their end. NASA expects their instruments to function until around 2025, after which they will gradually shut down. Even after losing contact, the spacecraft will continue their journeys through interstellar space. Voyager 1, moving at 3.5 astronomical units per year, is headed toward the constellation Ophiuchus, while Voyager 2, traveling at 3.1 astronomical units per year, will approach a star in the Andromeda constellation in about 40,000 years. Though the Voyagers have left the heliopause, they have not yet exited the solar system. The true boundary is believed to be the Oort cloud, a vast spherical region of icy bodies surrounding the solar system. It will take Voyager 1 about 300 years to reach the inner edge of the Oort cloud and possibly 30,000 years to traverse it entirely. Both spacecraft carry messages for any extraterrestrial life they might encounter. These include a gold-plated phonograph record with music, greetings in various languages, and sounds from Earth. Whether or not they are ever discovered, the Voyagers will remain silent ambassadors of humanity, traveling through the vast darkness of interstellar space. They serve as enduring symbols of our quest for knowledge and the dreams of a small, pale blue dot called Earth. The European Space Agency's Gaia Space Observatory has made significant discoveries about the environment in which our solar system resides. One of the most remarkable findings is the identification of the local bubble, a massive, nearly spherical void in the interstellar medium. This bubble is not a static feature of space, but is expanding at an impressive rate of about 4 miles per second along its outer surface. The origins of this bubble date back millions of years and are linked to a series of supernova explosions. Supernovae are some of the most energetic events in the universe, where a dying star explodes, releasing vast amounts of energy and material into space. These explosions expelled gas and dust from their surroundings, creating a low-density cavity. This process left behind the local bubble, which is surrounded by a dense shell of compressed gas and dust. The surface of the local bubble is a fascinating region. It is here that astronomers have identified 7 distinct zones where conditions are just right for the formation of new stars. These regions are composed of dense molecular clouds, which act as the raw material for star formation. Interestingly, the star-forming activity is concentrated along the bubble's surface rather than within its interior. This is because the interior of the bubble is relatively empty, having been cleared out by the force of the supernovae that created it. The dense material along the surface, compressed by the expansion of the bubble, provides the perfect environment for stars to form. This dynamic interplay between destruction and creation highlights how catastrophic events like supernovae can ultimately lead to the birth of new stars and planetary systems. The local bubble is not an isolated feature. Similar bubbles are scattered throughout the Milky Way galaxy, each formed by the energetic explosions of massive stars. These bubbles play a crucial role in shaping the structure of the galaxy by redistributing gas and dust, triggering star formation in some regions while leaving others devoid of material. It is likely that other stars, and possibly entire planetary systems, exist within their own bubbles, each shaped by the unique circumstances of their formation. The local bubble is just one piece in the vast and complex puzzle of our galaxy's evolution. The Sun's position within the local bubble is particularly noteworthy. The supernova explosions that created the bubble occurred far from the Sun's original location. When these explosions happened, the Sun was approximately 1,000 light-years away. Over millions of years, as the Sun moved along its orbit around the center of the Milky Way, it gradually entered the central region of the local bubble. This migration happened around 5 million years ago, and evidence for this timeline comes from the discovery of radioactive isotopes in Earth's crust. These isotopes are remnants of the supernova explosions and provide a direct connection to the events that shaped the bubble. Their presence on Earth serves as a record of the cosmic forces that have influenced our solar system over time. The structure of the local bubble can be visualized as being similar to the holes in Swiss cheese. Supernova explosions create cavities, or bubbles, in the interstellar medium, which are surrounded by shells of gas and dust. These shells, formed by the compression of material during the explosions, are where star formation is most likely to occur. The surfaces of these bubbles are rich in the elements needed to form new stars, while the interiors are relatively empty. Astronomers are actively mapping these bubbles throughout the Milky Way using advanced telescopes and three-dimensional mapping techniques. This work is helping scientists understand how these bubbles interact with each other and how they contribute to the life cycle of stars and the overall evolution of the galaxy. The arrangement of our solar system within the local bubble adds another layer of complexity. At the center of our solar system is the Sun, a massive, luminous star that is the primary source of energy for Earth and its neighboring planets. Surrounding the Sun are the 8 planets, each following its own elliptical orbit. These planets range from Mercury, the closest to the Sun, to Neptune, the farthest. The outermost planet, Neptune, is located approximately 4.45 billion kilometers, or 30 astronomical units, from the Sun. Beyond Neptune lies the Kuiper Belt, a region filled with icy bodies and dwarf planets like Pluto. Even farther out is the Oort cloud, a spherical shell of icy objects that marks the boundary of our solar system's influence. The local bubble itself is embedded within the Milky Way galaxy, a vast spiral galaxy containing billions of stars, planets, and other celestial objects. Our galaxy is a dynamic and ever-changing system, shaped by the forces of gravity, stellar evolution, and the interactions of interstellar matter. The local bubble represents just one of many features within this complex environment, offering a window into the processes that govern the formation and destruction of stars and the distribution of matter in the universe. By studying the local bubble and similar structures, astronomers hope to gain a deeper understanding of the cosmic forces that have shaped our galaxy and continue to influence its evolution. This research not only enhances our knowledge of the universe but also provides valuable insights into the history and future of our own solar system.